4. Inferential statistics. So this comes from the result of the data analysis, where it can give you inferential statistics and can give more depth of information from these statistical tests. The inferential statistics assesses the ability of expected an outcome, so the probability of the other result recurring. This could be for a future point of a result. It can be used for testing within a population to give a general order and generalize the population to give a broader result within the testing population. It's also used for showing the meaning of the data instead of just describing what the data is, and it shows whether the data accepts or rejects the null hypothesis, and this is done by the result of the inferential statistics, therefore showing significant difference or correlation within a data set. So there's commonly used in quantitative research is through the use of statistical tests. Statistical tests can be used to measure relationship or difference between a sample group and or a sample set. Also, when testing, there's a level of significance. This is to see if there is a correction or difference, and if this is linked to luck or chance, because you might get a really good result and it might just be luck, or it might actually be really what happened through your results, and to the test being more correct and trustworthy and credible, whereas just getting a lucky chance by fluke or just by a one-off. Statistical testing is using your data to find out what the data is and find out if the data is parametric or non-parametric data, and this means it shows if it's normally distributed or not normally distributed data, if it's difference or correlation, the classification of data to show if it's continuous data, and if within the research if they used match pairs, so it's the same participants, or independent groups, which is a group of different, to find out what type of data and how your data is going to be used within your test to link your results, and that you will use a tree diagram and follow it along, answering yes or no questions to see if your data represents one of these. So as you can see, this inferential statistics tree diagram shows what way or what type of data you'll be using and what test you've used to get this result. So as you can see, you have the differences, the correlation, and the categories, and you follow it to see where you get. It shows the parametric and the non-parametric. So parametric test is where the data is normally distributed and it's continuous data. So this is this bit here with the parametric and non-parametric under the same and different subjects. And then non-parametric is not normally distributed data, and this means that it's ordinal data, which means the data is ranked. There's also a test for difference. This test for difference shows the mean of two groups or two conditions. So this means that the groups were either different groups under the same conditions or the same groups under different conditions, working out the results there. So, yeah. An example of this linked to gymnastics could be between gymnasts and non-gymnasts. So it could be the amount of dismounts stuck between gymnasts and non-gymnasts to see the difference between the two categories. It could be repeated measures, so this means that the same participants or group of people are complete the same test in different environments. So an example of this could be the difference in a floor routine score with an audience. This would be at a competition, or without an audience at a training session. The means of the gymnast scores with and without an audience would be compared to see the difference. Linking this to the parametric and non-parametric test, if you had the same participants or same matched pairs groups, you would use a dependent test or a paired t-test. Whereas if you were or if you had two or more groups, you would use an independent paired t-test. For non-parametric, if you had the same subjects, the same matched pairs, you would use the Wilcoxon matched pairs t-test. Whereas if you had two or more groups and were comparing the mean, you would use the Mann-Whitney U-test. Within this, you would simply just follow the direction of the tree diagram to the decision tree to see which test you were going to do. So most of the time, we would use either differences or correlation, but sometimes it might be categories. You would follow the bottom bit and do chi-square test. But because our data is going to be continuous, so I'm going to be differences or correlation. So if we were doing a correlation graph, we would see whether it was parametric or non-parametric. So whether it was normally distributed or non-normally distributed, continuous or ordinal data, and then it would give us a test to do. With differences, we would see how many factors there were within the test. So if there was two or more factors, we would do this test, the last one here. If there's only one factor, which is likely to be, we would see if within our test we used the same or different subjects. This was either matched pairs or independent group. So if we had the same, we'd go back to this non-parametric and parametric decision to see if our data was normally distributed and continuous, so that means it would be parametric, and we'd use the paired t-test. Whereas if it was non-parametric, we would see that the data is not normally distributed and it's ordinal data, so we do the Wilcoxon paired test. However, if we use different subjects when testing our test, we would still go back to this non-parametric and parametric, but if it was parametric, we'd use the t-test, or if it was non-parametric, it would be the Mann-Whitney. When testing correlation, it tests if there's two or more variables and if they're affected, as well as showing the relationship between these. As explained in the previous videos, it gives an R value, so R will either be +1 where it's positive strong correlation, or -1 where it's a strong negative correlation, whereas in the middle is quite weak. So for example, if we were doing a test for linkage gymnastics with linkage correlation, so we would see if PNF stretching had an effect on the flexibility of a gymnast, which will allow them to be able to perform better skills and be able to, for example, their leaps will become more higher and at a higher angle, and their splits in general. Parametric test and non-parametric test. If you were doing a parametric test, so if the results were nominal, the data was normally distributed, you'll be doing the Pearson's product moment correlation test, and this is related to mean if the same or matched pairs, and this will give you an R value. Whereas if you're doing the non-parametric test, you're doing the Spearman's rank order correlation test, and this also gives you a R value for the test, positive or negative. Significance is the level of significance from the data, or the p-value. So the p-value is normally less than 0.05 and is set by the researcher before the data is collected. So when the data is collected, if it is less than 0.05, the data and the results is significant. Whereas if it is more than 0.05, the research is not significant, meaning it could be unreliable and is incorrect. Whereas if it has a high level of significance under 0.05, it's trusted. Practical significance is whether the results are useful in the real world. It also looks at whether the difference is large enough to be a value of practical sense.